One of the classic problems that led to the development of calculus is that of calculating areas. Now we're going to just estimate them. But geometry dealt with a lot of, areas of circles and squares and polygons and whatnot. But when the shapes get more and more complicated, it gets tougher to do. And that's what mathematicians were trying to do when they started developing these notions of calculus. So the area that we're looking at is something along the lines of this, that you've got a function, some y equals f of x, and you've got some starting point, x equals a, and some ending point, x equals b. And for the sake of argument here, I'm drawing this function always positive. In later videos, we'll consider what happens if it's negative. But this way it really looks like an area. Above the x-axis, below the function, between x equals a and x equals b. The question is, what's that area? Now, if this is a nice straight function, we can probably figure it out. Of course, if it's flat, all you got is a rectangle. If it's slanted, then it's not a parallelogram, it's a trapezoid, and we can calculate the area of the trapezoid. So the trick comes in, what do you do when it's curved, when the top is curved here? How do you calculate the area? Well, this is a theme that we will see over and over again this quarter, and that what we're going to do is we're going to chop it into a bunch of little pieces, estimate the area of the little pieces, and add them all up to get an estimate of the whole area, and then do it again with more pieces and see if we can get a better estimate, and then more pieces. So here's the idea. Let's see. Let's write this up. Chop up and approximate. And you can put as many p's in approximate as you want. I don't know how many there's supposed to be, so there we go. So the idea here is, no, let's do this with an actual example. So I want to start with a function here. Let's go right here and say, let's look at y equals x squared, and I'm going to look at the interval from 0 to 2. Okay, so go ahead. I'm going to stretch it out just so I can see a little better what's going on here. So at 1 the height is 1, at 0 the height is 0, and at 2 the height is 4. So it goes all up to 4 there. So the scale is not the same left and right, up and down at the moment, but anyway, you get this parabola, y equals x squared. Now, I'm going to chop this into 4 sections. So I'm actually looking at the interval 0 to 2 on the x-axis, down here on the x-axis. I'm going to chop that up into 4 pieces. Now, they don't have to be equal pieces, but it turns out that it's convenient, make some calculations easier if you do chop them into 4 equal pieces. So if I chop that into 4 equal pieces, this was 2, this was 1, well, if they're equal length there, each one of these pieces has to be a half. So this is 1 half, this is 2 halves, this is 3 halves, this is 4 halves. Let's write that actually as a half. In the x direction here, each little subinterval has length, the total divided by the number that I'm chopping by. So I have n equals 4 here, and that width I'm going to call delta x. That is, delta is often used to indicate a change, so the change in x from one x value to the next that I'm interested in here is the total length, so 2 minus 0 divided by 4, and that's a half. And so there I can get my x values that way. Starting at 0, move over half, move over another half, and another half, and another half, and you got those x values. Now, I'm trying to estimate the area underneath that curve over the x-axis. And I'm going to chop it up into these sections using those x values. So the widths are all the same here. But the thing is, I have still slanted heights. And I need to make a choice as to how am I going to decide what height to use. Well, there's different ways you can choose, and I'm going to choose for each interval here, I'm going to choose the right-hand end to see how tall it is. So on this first interval, I'm at the right, it's this tall. So I'm going to think of a rectangle that's that tall. And then the second interval, I'm using its right-hand endpoint. And the book's notation here um, would say I'm using right hand cutting into 4 pieces. So every interval I'm using the right hand endpoint. In this example, because x squared is always increasing for positive values of x, the right hand endpoints are always the highest. And so I'm definitely overestimating here because each of these rectangles is taller than what the function actually is. Okay? So R4, what we're going to do is we're going to multiply the height times the width of each rectangle. So the first rectangle is, the width is a half, and the height is whatever you get when you plug a half into this graph of y equals x squared. So I need a half squared. And then I'm going to add on to that the area of the next rectangle. Well, the next rectangle still has width a half, but now the height is whatever you get when you plug a 1 into the function. Well, you're going to take 1, plug it into the y equals x squared here. That's 1 squared. And then I'm going to add on to that the area of the next rectangle. So this is, again, width of a half, but this time the height is determined by plugging the 1.5 in to the function here and getting whatever that height is. So that's 3/2 squared. And then lastly, I'm looking at this last rectangle with a width of a half and a height of whatever you get plugging a 2 in. Well, 2 squared is going to be 4. So I end up with an estimate of, what do we have? 1/2 times a fourth, that would be an eighth, plus 1/2 times 1, that would be a half, plus 1/2 times 9/4, so that would be 9/8, and then 1/2 times 4, that would be 2. For grand total, added up, 9/8 and 1/8 is 10/8, so that's actually 5/4, and then here's 2 more fourths, so that would be 7/4. So 2 and 7/4, which would be 3 and 3/4. Okay. Now we know that that is too big. That definitely there's too much area is underneath it. So let's try again and get a smaller estimate by using the left-hand endpoints. So for the left-hand endpoints, I'll call this L4, again, left using 4 subintervals. So on this first interval, I'm going to use the left side to see how high it is. Well, the left side, the x value is 0. If I plug the 0 into the x squared, well, 0 squared is 0. So the width is a half, but the height is 0. Actually, I'm going to do this in a different color so that we can see this. I'm going to go with red here. So for that first interval, that's really short. So this is 1/2 times the height of 0 squared. And then on the next interval, I'm using this height right here. So this is my subinterval, my second subinterval. I'm using the left end to plug in and see how tall it is. Right? So that would be still a width of a half, but the height now is a half squared, plus the next one, so this width times that height. So that height there was plugging the 1 in, so the width of a half. I get the height by plugging 1, the value of x equals 1 into the function, so squaring 1. And then lastly, I've got this last subinterval, has width a half, it has height, whatever I get when I plug in 1.5. And so now I've got 0 plus, that's an eighth again, and this is a half, and this is 9/8. So that would be 10/8, plus that would be 14/8, which would be 7/4, which would be 1 3/4. So from this calculation, I would say that the area is somewhere between 1 3/4 and 3 3/4. If I want to do better than that, then I have to chop it up into more pieces. Now, I think what I'm going to do here is I'm going to stop this video at this point, and we'll talk about the general chopping it up into more pieces in the next video.